Okay, doke. About that time? Well, good afternoon, everybody. Hope everybody's doing well this afternoon. Hope everybody's having fun during the quarantine. Again, as always, let me start by apologizing that this happened. Obviously, this is not the best way to do our class this way, but we're just going to all have to do the best we can with what we've got. So, this is. Why is it underlined? Nobody knows. This is Psychology 301. Research, design, and methodology. And today is April 6th, 2020. And what we are going to do today is review for midterm number 2. So I'm going to hold this like a review session here, sort of like if we did the one at night rather than the one during the day. Excuse me. So, oh God. Okay, and so what's going to happen is I'm going to do the review session like we do at night, where I go over everything. I usually don't go everything on the review sheet during the day review sessions, but the ones at night I do. So this is probably going to go a little bit longer because that's the whole purpose today, is to review for midterm 2. Got a lot of good feedback about the pictures. People like Rosie's picture, so here's another picture of Rosie when she was a little puppy today. Okay, well, let's talk about the review for midterm number 2. Let's talk about midterm number 2. Midterm number 2 will be available starting at noon on Wednesday, April 8th. And it will shut down at 1 p.m. on Thursday, April 9th. Okay, so, and it's a 30-minute multiple choice and fill in the blank test. So, really can't have a short answer test this way, so we're going to have to switch from our normal test format to a multiple choice test. Now, what I'm going to do, how this is going to work, is that there are going to be, there's going to be 30-minute multiple choice and fill in the blank test. Yeah, 30 minutes, and there are going to be 40 questions. 40 questions in 30 minutes. Now, the 30-minute time limit is very strict. As soon as you start it, the 30 minutes are going to start. And so please be someplace where you're kind of not going to be interrupted and where you actually have 30 minutes to take the test. Because once you start the test, you're on the clock. And so you'll only get credit for as many questions as you can answer once you have started the test. Now, I said earlier, this is going to be, I don't see any way I can prevent you from looking at your notes. I mean, I could say don't look at your notes, but I know there'd be some people who'd be honest and wouldn't look at their notes, and then there'd be some people who'd cheat and would. So that doesn't seem fair, so to the people who are honest. So, deal is that you can look at your notes, but I don't think, since you got to answer 40 questions in 30 minutes, you're really going to have time to look up the answers very often. So you'd have to be very lucky to actually have enough time and be able to look up the answer. And also to discourage you from looking up the answers in the notes, there are going to be more of the questions you have to think about, like what type of stats analysis is appropriate, which is this, what type of quasi-experiment or single-subject design is this? Is this an experiment or an investigation? Those type of questions, they are more likely to be on this test than they would be if I were doing the test during the regular class period. So I won't ask you to write out the definitions for any of those definitions in the definitions section. I can't really do that. And and so a lot and more emphasis, like I said, on the kind of questions you have to think about. But then there'll be some other just rote memorization questions. But here's what I wanted to say. If you have studied using note cards, using the review sheet for midterm number 2, which is on the front sheet of the Canvas site, if you have studied using note cards, like I said, like it was one of the short answer tests, like midterm number 1, then you should get all the questions right on midterm number 2. If you know how to do all the skills and things, you should be okay with midterm number 2. And so how this is going to work, so you are allowed to look at your notes, but, I don't want to hear any complaints afterwards. Hey, there wasn't enough time to look up all the answers in our notes. Well, that's right. I'm not forbidding you to do it, but I am trying to make it hard for you to do it, I'll admit. And so, no, there's probably not going to be enough time to finish the test and look up all the answers in your notes. That's why I want you to study for it before you take it. So, anytime, you can take it anytime between noon on Wednesday, April 8th, and then it's going to totally shut down at 1 p.m. on Tuesday, April 9th. So I guess the latest you could start it would be 12:30 on Thursday, April 9th, if you want to have your full time. Okay, well, what I'm going to do today is we're going to try and practice some of the skills that you have to have for the test. And we have a new skill, and make sure you wait around to learn the new skill. The new skill that I'm going to teach you today is interpreting an ANOVA summary table. So make sure you go through that. Everything else will be pretty much review, I think. But we'll have a section in a second on interpreting this ANOVA summary table. But let's go through. I want to practice each of the skills that you have to know. And so the first set of skills is identifying statistical tests. Identifying statistical tests, please, is going to be the first skill that we learn today. I'll underline that so we know where we are. All right, so let me put up a description of how somebody did their research, and then you have to tell me what sort of stats analysis they did. Now, we know a lot. We only knew 4 stats analyses last time. Now we know 9, and the 9 are the test of a single sample mean, the between subjects t-test, the within subjects t-test, the between subjects one-way ANOVA, the within subjects one-way ANOVA, the between subjects factorial ANOVA, correlation, the between subjects variance test, and the within subjects variance test. You know all those 9 tests. And so there'll be several questions in the pool. You're going to get, I should say, there'll be a pool of questions. You'll get 40. This is to discourage you from using another person. Using another person on the test is definitely against the rules. And to discourage you from doing that, your questions aren't going to be exactly like other people's. So I'm going to have probably a set of 100 questions, and you're going to get 40 of those randomly. Okay, so let's try the first one of the stats analysis questions. Yep. All right. Make it a little bit bigger here. All right, do vitamin C, vitamin E, vitamin A, and vitamin D differ in their mean effects on people's math performance? 20 subjects are randomly assigned to be in either a vitamin C group, a vitamin E group, a vitamin A group, or a vitamin D group. In other words, there are 5 subjects in each group. After taking their vitamins for a week, the subjects are given a math test. We're interested in whether the means of the 4 groups differ reliably. What's the appropriate sort of stats analysis? All right, what do you think? The answer is the between subjects one-way ANOVA. Between subjects one-way ANOVA. That is the answer, and the reason is we have more than 2 IV levels. We got 1, 2, 3, 4 IV levels. Each subject is assigned to one of the 4 IV levels, and then we're comparing the means. So that means it's a between subjects design, where we're comparing the means. And so more than 2 IV levels, that's why it's between subjects one-way ANOVA. All right, let's do another one. Yeah, you want to know if 5th graders are better at doing multiplication than 3rd graders. Give a multiplication test to a group of 6 randomly selected 3rd graders and 7 randomly selected 5th graders, and you want to do an analysis to see if the mean scores differ on the multiplication test. What sort of analysis is appropriate? What you think about that? The answer is the between subjects t-test. Between subjects t-test. Reason is we got 5th graders and 3rd graders, so we've got different people assigned to each IB level. You can't be both a 3rd grader and a 5th grader. And we want to compare the means, so we got 2 levels of our independent variable. We're comparing the means, so that's, and it's a between subjects design, that's why it's the between subjects t-test. All right. Next on the hit parade. Test is done to determine if people like Sprite better than 7-Up. 5 subjects are given tastes of Sprite and tastes of 7-Up, and they rate how much they like them on a 10-point scale, where 1 is poor and 10 is excellent. We want to know if the mean ratings for Sprite and 7-Up are reliably different. What's the appropriate type of stats analysis? What do you think about that? Answer is within subjects t-test. Within subjects t-test. Why is it within subjects t-test? Well, our subjects got both levels of the independent variable, right? They got the 7-Up and they got the Sprite, so that's why it's within subjects. It has 2 levels, and we're comparing the means, so that's why it's the within subjects t-test. All right, let's do another one. Experiment was conducted to determine the effects of amount of sleep, 4 hours versus 8 hours versus 12 hours, and test time, morning versus evening, on memory. 24 subjects are randomly assigned to one of the 6 treatment combinations, and their score on a memory test is recorded. We're interested in the effects of the variables on mean performance. What is the appropriate sort of stats analysis? A second to think about that. Okay, that's the between subjects factorial ANOVA. This one you should have known from the very first sentence it was between subjects factorial. As you can see, it has 2 independent variables, amount of sleep. It has 3 levels, 4 hours, 8 hours, 12 hours, and test time, morning versus evening, on memory. 24 subjects. So it's the only analysis that we know that has more than one independent variable, and so that's why it must be the between subjects factorial ANOVA, because it's got more than one IV. All right, next on the hit parade. You're interested in whether IQ scores and GPA are related. You get both the IQ and high school GPAs for a group of 8 people and want to determine if there is a relationship between the two. What's the appropriate analysis for this data? And this should be an easy one. Answer is correlation. Correlation. You're looking for a relationship. Want to see if there's a relationship. That tips you off that it's a correlation problem. Correlation problem. Okay, next problem. Zabadoozy. Experiment is conducted to determine if people's ability to remember verbally presented lists of words changes when the words are read at 3-second intervals, 6-second intervals, or 9-second intervals. 7 subjects are read lists of 20 words at each of the 3 different time intervals, and the number of words they could remember from each list is recorded. We're interested in whether the means at each of the 3 intervals are reliably different. What is the appropriate sort of stats analysis? Okay, give me a second to think about that. Answer is within subjects one-way ANOVA. Within subjects one-way ANOVA. We had 3 levels of the IV, 3-second intervals, 6-second intervals, 9-second intervals. So our subjects are read 20 words at each of the different intervals, so that's how we know it's a within subjects design, because every subject received all 3 intervals, and we're comparing the means, so it's within subjects, more than 2 IV levels, and we're comparing the means. That is a between within subjects one-way ANOVA. All right, next. We are interested in whether having music in the background affects the variability in performing a memory task. Subjects are randomly assigned to be in one of two groups, a music group or a silence group. We want to know if the variances for the two groups differ reliably. What is the appropriate sort of stats analysis? Okay, give you a second to think about that. And the answer is the between subjects variance test. So each subject was randomly assigned to be in one of the groups, the music group or the silence group. That's what tips us off that it's between subjects. We had two levels, music group and silence group, and it asked us to compare the variances to see if the variances were different. So that's how we know it's the between subjects variance test. Between subjects designs with two levels, and we're comparing the variances. All right, next one. You hear on TV. The average person in Canada watches 5.3 hours of television a day. Randomly select a sample of Americans. Ask them how many, it should be hours of TV they watch per day. We're interested in whether the mean number of hours of television viewed differs between Canadians and Americans. What's the appropriate sort of stats analysis? And the answer is test of a single sample mean. Test of a single sample mean. Spell it right. Sample mean. Sample mean. There we go. Because we had a single number here where we don't have the sample. Comparing the mean of our sample of Americans to that single number. And so that's why it is the test of a single sample mean. Okay. Sugar. All right, one more. I'm just going to read this one. We're interested in whether sugar affects the variability in people's motor control. 6 subjects eat a cup of sugar and perform a motor control task. And later, these same 6 subjects consume no sugar and perform the same task. We're interested in whether the variance in the sugar condition differs from the variance in the no sugar condition. What's the appropriate sort of stats analysis? Okay, and the answer is that's the within subjects variance test. All subjects got both levels of the independent variable. That's what it makes within subjects. There is 2 levels, and we're comparing the variances, so that's why it's the within subjects variance test. Okay, well, I hope those went pretty well for you. There should be, I'm going to have quite a few of those on the test probably, because again, they're ones you have to think about, and I'm having ones to think about. Ones you have to think about are going to be more represented on the test. All right, now it's time for our brand new skill that we have not had before. So here we go. The new skill is interpreting an ANOVA summary table. We've done a bunch of ANOVAs in class, and the thing about the ANOVAs is you should be able to know a lot about the experiment that was conducted just by looking at the summary table from the ANOVA. And so there are going to be questions on the test where I give you an ANOVA summary table, and then I ask you questions about the table. So that's what we're going to practice now. I got an ANOVA summary table here. Yep. And of course everything got messed up. Why did it do that? I wonder. Alright, so let's see. We're going to try and make our margins a little bigger. Stop it. 0.5. Alright, it's going to be 2.5. Okay, there we go. It's better anyway. Bop, bop. Alright, there we go. There's an ANOVA summary table that we can read. And so, here's an ANOVA summary table from an experiment. First thing I'm going to ask you about this ANOVA summary table is what sort of ANOVA was conducted to create the table? What sort of ANOVA was conducted to create the table? Give you a second to think about that. All right, well, the answer here is it's the within subjects one-way ANOVA. Within subjects one-way ANOVA. How do I know that? Well, sorry, no, I copied the wrong one. That's not the one I meant to copy, but so no, that's wrong. This is the between subjects factorial ANOVA. I meant to copy the within subjects one-way ANOVA. I copied the between subjects factorial ANOVA. Let's copy the one I went to copy, huh? And we'll come back to that one in a second. I want to do the one I meant to copy. The one I meant to copy, I'm very sorry, is this one. There we go. All right, what sort of ANOVA was done to create the table? Well, the answer here to this one, let's look at it for a second. This is the within subjects one-way ANOVA. This one is. And how do I know that? Well, it has 4 lines. It also has a subjects line and an error line. Remember, the only one with an error line is the within subjects one-way. The others, bizarrely, the between subjects ANOVAs have a within line. The within subjects ANOVA does not. The easiest way, there are a number of ways, but if the ANOVA has 3 lines, then that is going to be the between subjects one-way ANOVA. If it has 4 lines, that's going to be the within subjects one-way ANOVA. And if it has 5 lines, that's going to be the between subjects factorial ANOVA. I think that's the easiest way to do it, is just remember those. Okay, so I'm going to keep that up there. I'm going to erase it in a second. There's the second question I might ask you about the ANOVA. That is, was a particular effect reliable? Was a particular effect reliable? If it's with one of the factorial ANOVAs, I'm going to ask you about either of the main effects or the interaction. In one-way ANOVA, of course, I'll just ask you about the independent variable. So, did we get a reliable effect of the independent variable in this ANOVA table? I'll let you think about that. And the answer is yes in this one. So, the answer is yes. Yes, if P is less than 0.05, comma, no, if P is greater than 0.05, comma. So what you do is you look at the P value over here. If it's less than 0.05, yes, it was a reliable effect. If it's greater than 0.05, then it's not. All right, I'm going to erase this question, move the other up. Okay, next question I might ask you is, how many levels did a particular IV have? How many levels did a particular IV have? Of course, it was a factorial design. I'd have to tell you what IV, but here we only have one IV. So our independent variable here is food nationality. Question for you is, how many levels did that have? Okay. And the answer is, what you do is, if you remember, the degrees of freedom for your independent variable, df treat, is the number of levels minus 1. So if your degrees of freedom is 3, well, that means that your levels were 3 plus 1. So here's how you do it. Apply number of levels equals degrees of freedom plus 1. Degrees of freedom plus 1. That's going to be your number of levels. And so food nationality is our independent variable. It has 3 degrees of freedom. We add 1, and we get 4. So the answer would be 4. All right, next question. How many DF did a particular F ratio have? How many DF did a particular F ratio have? So our F ratio here is 49.25. How many degrees of freedom does that have? Well, you know all F tests have 2 degrees of freedom associated with them. one with the numerator and one with the denominator. So the numerator df is df for the effect, whatever effect I'm asking you about. In other words, it's on the same, the df on the same line as whatever I'm asking about. So here's our f ratio here, and so the numerator degrees of freedom is going to be one on the same line here. That's 3. Now the denominator, I did not do that. The denominator degrees of freedom, denominator df equals df error or df within, depending on, maybe I should put a space. So df error in this one, within subjects, or df within if it's a between subjects. So here's our error line. You can see it's got 12 degrees of freedom. So that's going to be the denominator degrees of freedom. Now, if this were a between subjects ANOVA, this would be a within line here. It's the one above the total always. And you're going to look at the degrees of freedom, and whatever those degrees of freedom would be, that's the denominator degrees of freedom. So how many df did a particular f ratio have? Our f ratio, 49.25, has 3 degrees of freedom in the numerator and 12 degrees of freedom in the denominator. That's what this one is. All right, I'm going to erase these two and go to the next question. Next question I might ask you is, what two numbers in the chart were divided to get a particular f ratio? What two numbers in the chart were divided to get a particular f ratio? So our f ratio is 49.25 here. There were two numbers in the chart that we divided to get 49.25. I want to see if you remember what those are. All right, so the numerator is going to be ms for the effect, whatever effect I'm asking you about. So it's on the same line as the f ratio. So in this case, there's only one f ratio, so you don't have to worry about that. So 17.73, that's the number in the numerator. And why does it do that? And then the denominator, what that's going to be is ms for error, or ms for within. If it's a between subjects ANOVA, you do ms within. So ms error, that's 0.36. So this f ratio, 49.25. The numerator was ms for the effect, that's 17.73. The denominator is going to be ms for error. We have an error line rather than a within line here. Because it's within subject design, that's 0.36. So 17.73 divided by 0.36 is 49.25. Okay, last question I could ask you about the F table would be, what two numbers in the chart were divided to get a particular ms, particular mean square? What two numbers in the chart were divided to get a particular mean square? So here's mean square treat. Mean square for food nationality is 17.73. There were two numbers in the chart we divided to get 17.73, and I'm asking you what two those are. So the numerator in that question, the numerator is going to be SS for the effect, whatever effect I'm asking about. In this case, it was food nationality. So sum of squares there is 53.2. That would be in the numerator. The denominator is going to be SS, not for the effective. Stop that. Is going to be DF for the effect, whatever one I'm asking you about. In this case, I asked you about food nationality, so that's 3. So if you remember, I said this about 1 billion times when we were doing the ANOVAs. A mean square is always a sum of squares divided by degrees of freedom. So if I want to find MS for food nationality, well, that's SS for food nationality, 53.2 divided by 3 is 17.73. What if I asked you what two numbers in the chart were divided to get MS subjects? MS subjects is 6.33. So that would be SS subjects, 25.3 divided by 4 is 6.33. If I asked you, how did you get MS error? What you do is you take SS error, 4.30, divide by DF error, 12, and you get MS error, 0.36. All right, well, I hope you got those down in your notes. We're going to try some others now. Hope you got all that down. All right, now I'm going to erase this and do some other tables. So let me put up that table I put up earlier and didn't mean to put up. I apologize for that. Put up this one now. Here we go. All right, so first question for you about this one is, what sort of ANOVA was done to generate this table? Okay, and the answer is the between subjects factorial ANOVA. Between subjects factorial. How do you know that? Well, it's got 5 lines here. 5 lines. It's the only one with 5 lines. It also has this interaction line. It has the two independent variables, a little x between them. And that's the interaction line. And so that's unique to the between subjects factorial ANOVA as well. So if I asked you what sort of ANOVA was done to generate the table, you would say between subjects factorial. All right, next question is, did I get a reliable vitamin main effect in the experiment? Did I get a reliable vitamin main effect in the experiment? Well, here's the vitamin line for the vitamin main effect. I go over to the p-value. It's greater than 0.05. So the answer is no. If p is greater than 0.05, then you did not get a reliable vitamin main effect. Did I get a reliable training time main effect? Well, I go to the training time line. I go over to the p-value. P is less than 0.05. So yes, I got a reliable training time main effect. Did I get a reliable interaction in the experiment? All right, here's the interaction line. It's the line with the two independent variables and a little x between them. And you can see p there is greater than 0.05. So no, we did not get a reliable interaction there. Okay. All right, that's another question. All right, next question I could ask you. How many levels did the vitamin independent variable have? How many levels did the vitamin independent variable have? We'll answer that when I go to the vitamin line. I go over to the degrees of freedom here, and I just add 1. So you add 1, and so we know vitamin had 2 levels. What if I asked you how many levels did the training time independent variable have? Well, you go over here to the training time independent variable, go to the degrees of freedom, you add 1, and so it had 2 levels as well. All right, so that's the second question I could ask you. Or third question I could ask you, I guess. Okay, fourth question. How many degrees of freedom did a particular F ratio have? In this case, how many degrees of freedom did the F ratio for the training time main effect have? How many degrees of freedom did the F ratio for the training time main effect have? All right, here's the F ratio for the training time main effect. So the numerator degrees of freedom is going to be on the same line. That's right here, 1. So it has 1 in the numerator. And then the denominator degrees of freedom is going to be on the within line, DF for within. It's always the one above total. It's the within line if it's a between subjects factorial. It's the error line if it's the within subjects one line. And so we can see the degrees of freedom for within is 16. So the F ratio for the training time main effect has 1 and 16 degrees of freedom. Okay, what if you were asked about the interaction? How many degrees of freedom does the F ratio for the interaction have? Well, here's the line for the interaction, right? Here's the F ratio, 0.08. And so the number of degrees of freedom is going to be this one, 1, divided by this one, 16. This one, 16. So that's the degrees of freedom there. Okay, I'm sorry, I had a little break there. I thought I paused it, but I didn't. There's something wrong with this chart, and that is this shouldn't be an F. This should be over here. So I apologize for that. All right, let's continue. Next thing we're going to ask is, what two numbers in the chart were divided to get the F ratio for the vitamin main effect? What two numbers in the chart were divided to get the F ratio for the vitamin main effect? Well, here's the F ratio for the vitamin main effect, right? And so it's going to be the mean square for the effect, 1.80, over ms within, and this should have been over, this is ms within here, 10.38. So 1.80 in the numerator, 10.38 in the denominator. This one divided by this one, that's 0.17. What if I asked you what two numbers in the chart were divided to get the F ratio for the training time main effect? Well, here's the F ratio for the training time main effect. So the number in the numerator is going to be mean square for the effect. That's this one, the one on the same line, 2,247.2. And that's going to be divided by mean square within, 10.38. So 2247.20 divided by 10.38, that's 216.49. All right, last questions about the chart. I'm going to ask what two numbers were divided to get ms within? What two numbers were divided to get ms within? What was the number in the numerator? All right, well, mean square is always sum of squares divided by degrees of freedom. So 10.38, that's ms within. So SS is 166.2, that's SS within. Divided by 16, that's degrees of freedom within. That's mean square within, 10.38. So mean square is always sum of squares divided by degrees of freedom. All right, one more of these. Let's do one more because it's a new skill and I want to have some practice with it. So we're going to make this one go away and put in our new one. That looks right. Zap that just for a second. Okay, here we go. So next questions I'm going to ask you are, what sort of ANOVA was done to create this table? Okay, and the answer is the between subjects one-way ANOVA. The reason is because we got three lines here, okay, and so it's three lines. That's the simplest one. That's the between subjects one-way ANOVA. Okay, next question is, how many levels did the independent variable have in this experiment? How many levels did the independent variable have in this experiment? So here's the line for the independent variable. Remember, we go and look at the degrees of freedom, and we add one. So it has 3 degrees of freedom, so that means there are 4 levels. State has 4 levels, okay? All right, next thing is our F ratio here is 0.49. 0.49. Next question is, how many degrees of freedom does that F ratio have? How many in the numerator? Okay. Well, here's our F ratio, 0.49. And so for the numerator degrees of freedom, we go over the degrees of freedom. It's on the same line as the F ratio. And then for the denominator degrees of freedom, we go above the total line. So that's here, the within line. So this F ratio has 3 degrees of freedom in the numerator, 16 degrees of freedom in the denominator. That's how many it has. All right, did I get a reliable effect of the independent variable in this experiment? Did I get a reliable effect of the independent variable in this experiment? And the answer is no. No, I did not. The reason is P is greater than 0.05. If P is greater than 0.05, then there was not a reliable effect found. All right, next one is our F ratio is 0.49. What two numbers in the chart were divided to get this F ratio, 0.49? What two numbers in the chart were divided to get the F ratio? What was the number in the numerator? And the number in the numerator is 1.13. It's the mean square on the same line as the F ratio. And then what was the number in the denominator? The number in the denominator was 2.28. It's the one in the within line, the one above total always. So 1.13 divided by 2.28 is 0.49. All right, last question I'm going to ask you for this one. MS for state. MS for state. What two numbers in the chart were divided to get MS for state? What was the number in the numerator? Okay, so MS for state, that's this one, 1.13. So a mean square is always the sum of squares divided by degrees of freedom. So numerator is going to be 3.4. And then the denominator is going to be SS for DF for state, that's 3. So 3.4 divided by 3 is 1.13. Similarly, if I asked you what two numbers in the chart were divided to get MS within, you say SS within, 36.4 in the numerator, and DF within, 16 in the denominator. Okay, so there'll be questions like that on the test, quite a few. What there'll be is there'll be a little blank space for you to type in the number if it's a numerical answer, so that won't be multiple choice. But there will be quite a few of these on the test because that's another one where you have to think a little bit, and I like those. So we're going to have some of those. All right, next thing we need to worry about, and what I'm worried about here is the quasi-experiments and single-subject design. So we haven't practiced those very much. We talked about those in class. I know it's been a long time since we had the quasi-experiments in particular. So what is going to be on the test, and again I mentioned there'll be quite a few of these because they're ones you have to think about and can't just write down from your notes. And so how these will work is I'll describe how somebody did their research, and then there'll be a multiple choice. You're going to have to pick out what sort of quasi-experiment or single-subject experimental design they used. And so these may be a little bit hard. Let's go over the 4 quasi-experiments first. The 4 quasi-experiments you need to know are the single-group pre-test, post-test design, the interrupted time series design, the non-equivalent before-after design, and the ex post facto design. So what we're going to do now is identifying quasi-experiments and single-subject experimental designs. Identifying quasi-experiments and single-subject experimental designs. That is our topic here. Okay, so we did the quasi-experiments. Single-subject experimental designs you need to know are the reversal design, the multiple baseline design, and the multi-element design. Reversal design, multiple baseline design, and multi-element design. All right, here we go. We are interested in whether our new method for teaching auto mechanics is more effective than the old method. We have 2 classes of students who are not randomly assigned to classes. One of the classes is in the day, and the other is at night. We give both classes a test of their knowledge of automobile repair prior to the class. We then teach the day class by the old teaching method and the night class by the new method. After the class is over, we give the automobile test again and use the difference in scores between the first and second tests as the dependent variable. What sort of design is being used here? Give you a second to think about it. Well, let's see. It has groups of people rather than single individuals, so we know it's a quasi-experiment. We have 2 separate classes who weren't randomly assigned, and we're giving a pre-test prior to IV manipulation and a post-test afterwards, and that is the non-equivalent before-after design. Non-equivalent before-after design. What sticks out about that is it's the only one with 2 separate groups of subjects where subjects weren't randomly assigned to the groups. That's probably what you should look for. It also, the dependent variable is the post-test score minus the pre-test score. That's going to be the dependent variable. That's another thing to look for. All right, let's do another one of these. Yep. We want to test a new gambling prevention program. We take a group of 20 chronic gamblers and measure the amount of money they spend gambling during a month. And a treatment is introduced to get them to stop gambling, and the amount of gambling is measured a month after treatment. What sort of design is being used here? All right, we got a group of subjects. We measured them once on the dependent variable before our manipulation and once afterwards. That's the single group pretest post-test design. Single group pretest post-test design. Got a group of subjects. That tells you that it's a quasi-experiment. And then the reason why it's a single group pre-test post-test design, you're using one group as their own control. That's what a time series design is like. And what you're doing is measuring the people once beforehand and once afterwards. And that's what a single group pre-test post-test design is like. In a single group pre-test post-test design, you measure subjects a single time before treatment and a single time afterwards. All right, next one. Yep. Why is it doing this? All right, doing this thing where it's underlining everything. We have 3 different treatments we think will reduce the noise a single disruptive child is making. For a week, we'd introduce a different one of the 3 treatments every hour and measure the amount of noise the child makes during that time period. What sort of design is being used here? Okay, well, it seems like a single subject design, right? It's only testing one child. We have several different treatments for one behavior, and that's the multi-element design. Multi-element design when you got several different treatments for one behavior in a single subject design. That's what we had there. Okay, next one. Again, I don't know why it's doing that. We want to test a new weight loss prevention program. Take a group of people who want to lose weight and weigh them once a week for 4 weeks. We then introduce our treatment. After the treatment, we again weigh each of the participants once a week for 4 weeks. What sort of design is being used here? Okay, so we got a group of subjects. That tips me off it must be a quasi-experiment. We're going to measure the people 4 times, more than once before treatment, and 4 times more than once after treatment. So that's the interrupted time series design. This is very similar to the single group pre-test post-test design. The only difference is in how often we're measuring the dependent variable. Remember, in an interrupted time series design, you measure it more than once before treatment and more than once afterwards. In a single group pre-test post-test design, you measure it only once before and only once afterwards. All right. Next one. We take 3 measurements on a single schizophrenic patient. Why is it doing this? We take 3 measurements on a single schizophrenic patient. The amount he screams, the number of voices he hears, the amount of time he spends catatonic. We introduce a treatment we think will reduce his number of screams. After introducing the treatment, we compare any changes in the number of screams he makes to changes in the other 2 variables. We then remove the scream reduction treatment and introduce a treatment for reducing the number of voices he hears, again measuring any changes relative to any changes in the other 2 factors. Then we withdraw that treatment and introduce a treatment for the amount of time he spends catatonic. And again, compare any changes in this variable to the other 2. What sort of design is being used here? Okay, well, we got a single subject design, right? Because we only got one person that's being tested. And then we've got several different behaviors we are measuring and one treatment for each. Several different behaviors and one treatment for each. And when you got several different behaviors and one treatment for each, that's the multiple baseline design. Multiple baseline design. Remember, in multiple baseline, you got multiple behaviors you're measuring. Very easy to confuse this with the multi-element design. In the multi-element design we discussed earlier, you've got several different treatments. The elements are the treatments. In a multiple baseline design, you have several different behaviors, essentially several different dependent variables you're measuring. That's what makes it unique. All right, next one. We have a single subject who has temporal lobe damage, and we're interested in whether we can improve the subject's ability to maintain fixation on a single spot. We first measure the length of time the subject can focus on a single spot. Then we introduce our manipulation. We give the subject a drug, and measure the subject again. We then introduce the drug again and measure fixations again. What sort of design is being used here? Okay, well, it is a single subject design because we're only measuring one person. And we got one treatment for one behavior. We measure them first without the treatment, then we give them the treatment and measure them again. We withdraw the treatment and measure them again. And then we give them the treatment and measure them again, and that is a reversal design. Reversal design. Reason why it's called a reversal design is we want to see if behavior reverses when the treatment is removed. That's why it's called a reversal design. So what you're looking for in the reversal design is one treatment for one behavior, and you're looking for a single subject design. All right, last one of these. We're interested in whether being in a city that's been hit by a tornado increases the amount of alcohol consumed in the city. Data is collected from liquor stores in a city that was hit by a tornado 3 weeks ago. Liquor store owners are asked for their gross income in the week prior to the tornado and in the week following the tornado, and the two values are compared. What sort of design is being used here? All right, we're using archival data to study an event that occurred in the past, and that is an ex post facto design. Ex post facto design when you're using archival data to study an event that occurred during the past. Okay, I expect there'll be quite a few of these on the exam because, again, I'm looking for things that you have to think about rather than just write down what you've memorized. And so I would expect quite a few of these to be on the exam, and I encourage you to learn those. Remember, I put down things to look for by each of them, so that's what I would spend my time studying if I were you. And let's go back to the top. Erase this. And all right, well, let's try the next skill we need to do is let's try the research evaluation questions. Research evaluation questions. Okay, well, let me give you things to look for in a research evaluation that might help you do better on these. So I'd look for regression to the mean. Why do you do that? I'd look for practice effects. I'd look for placebo effects. I look for you can't prove the null hypothesis. I'd look for confounds. And then 6, if a causal conclusion is drawn, was random assignment done? If a causal conclusion is drawn, was random assignment done? So, regression to the mean, practice effects, placebo effects, can't prove the null hypothesis, confounds, and then if a causal conclusion is drawn, look at whether a random assignment was done or not. If none of those are a problem, then it's probably okay. So, let's do one of these. Here we go. Yeah, over here. All right. Yeah. Okay, a new calculator has been designed, which will supposedly allow people to enter numbers more quickly than other calculators. An experiment is conducted to test whether this is true or not. We randomly select a group of 20 people from the general public and measure how much time it takes them to enter a set of 50 numbers into an old calculator, and then measure the amount of time it takes them to enter a different set of 50 numbers into the new calculator. We find that people have reliably faster mean times to enter the numbers into the new calculator than the old calculator. Conclusion is the new calculator allows faster number entry than does the old calculator. Is that conclusion justified? Is that conclusion justified? And I would say no, comma, practice effects. Notice everybody got Everybody got the old calculator first and the new calculator second. So they might have done better on the test just because they had some practice with the previous one, and so that might explain the results. All right, let's do another one. Okay. We're interested in whether people can remember more information if they study in a quiet environment than if they study in a noisy environment. We randomly assign 50 subjects to be either a noisy environment or a quiet environment. Each group of subjects reads the same magazine article and are told they'll be tested for their memory of its contents later. The subjects are given half an hour to read the article, and then they're each given a test with 20 questions to determine how much they remember. The group in the quiet environment gets an average of 19 out of 20 questions right, while the group in the noisy environment gets an average of 18.9 out of 20 questions right. The difference between the means is not statistically reliable. Conclusion is the amount of noise in the study environment has no effect on the amount people remember from magazine articles. Is that conclusion justified? I would say no, comma, can't prove the null hypothesis. Can't prove the null hypothesis. That is, they're saying in the conclusion, the independent variable has no effect on the dependent variable. And as we discussed, no matter what it says in the problem, if it says the IB has no effect on the DV, you know immediately that that is not justified because you can't prove the null hypothesis. All right, let's do another one. Interested in whether the Ames paper, the Des Moines paper, has better coverage of foreign affairs. We randomly select 12 people who subscribe to the Ames paper and 12 people who subscribe to the Des Moines paper and have each group take a test on current foreign affairs. We find that people who subscribe to the Ames paper have reliably higher mean scores on the foreign affairs test than people who subscribe to the Des Moines paper. Conclusion is people who read the Ames paper know more about foreign affairs than people who read the Des Moines paper. Give you a second to think about that. Is that conclusion justified based on our results? And I would say yes, the conclusion is justified. Yes, the conclusion is justified. And you're saying, what? They didn't randomly assign people to the papers. There might have been some other difference between the groups before we even started. So you didn't control for that. How can you say it's justified? Well, the question is this a causal conclusion? Let's read it. People who read the Ames paper know more about foreign affairs than people who read the Des Moines paper. Well, that's not saying it's reading the paper that caused them to have the difference. It's just saying that this group of people, people who subscribe to the Ames paper, know more about foreign affairs than people who subscribe to the Des Moines paper. That is justified based on the fact that we randomly selected people from each group and we found a reliable difference between them. That's what the reliable difference means, is that the mean for the people who subscribe to the Ames paper is greater than the mean for the people who subscribe to the Des Moines paper. So, because it's not a causal conclusion, it is justified. All right. Next on the hit parade. I want to know if people who get high scores on the ACT get better grades in college than people who get low scores on the ACT. We randomly select 300 college students and get their ACT scores and their GPA. We perform a correlation on the data and find a reliable, positive correlation between ACT scores and GPA. Conclusion is people with high ACT scores tend to have higher grades than people with low ACT scores. Is that conclusion justified? Answer is yes. The conclusion is justified. Okay, again, we're not saying that it's getting a high score in the ACT that's causing people to get better grades. All we're saying is this group of people, people with high ACT scores, tend to have higher grades than people with low ACT scores. Well, that is what a reliable positive correlation between ACT scores and GPA means. If you had to explain what a reliable positive correlation between ACT score and GPA means to somebody, you would tell them, well, it means that as ACT scores increase, the grades also tend to increase, and that's all we're concluding, so that is justified. All right, next one. We are interested in whether the tutoring program for the math classes at our university is effective. We take a group of people who flunked their first calculus test with an average grade of 53%. We assign them tutors to help them prepare for the second test. On the second test, the average grade increases to 71%, which is a statistically reliable improvement. Conclusion is the tutoring program is effective in improving people's grades. Is that conclusion justified? Think about this. Okay, I would say no, definitely no. The obvious thing to me is regression to the mean. That's the best answer, I would say. People did really badly the first time they took the test, and so the next time they take it, we'd expect them to get better on their own, even with, regardless, even if the program's completely effective. Now, I would say on these, of course, you're only going to be able to click on one, so I would click on the one you're most sure of. I would also give credit for practice effects. They had some practice on the first test, and also for placebo effects. They knew they were getting some sort of treatment, and so they might have gotten better just because of the treatment. So if you said either of those, I would take those as well. I think regression to the mean is the most obvious one. All right, one more of these. We've developed a new training program to improve people's memory. We randomly assign 60 people to be in one of two groups. An experiment group who receives our new training program, and a control group who receives a training program we know is ineffective at improving memory. After training, each group is given a list of 30 words to study for 10 minutes. After studying the list, subjects are told to write down as many words on the list as they remember. We find the group which received our new training program remembers an average of 24 words, and the control group remembers an average of 15 words. This difference is statistically reliable. Conclusion is the new training program is effective in improving people's memory. What do you think? Yes, it is justified. Yes, it's justified. All right, the new training program is effective in improving people's memory. Is that a causal conclusion? It is. It is, because it's implying that if you go through the training program, that will cause you to do better on the memory test. Now, to draw a causal conclusion, we have to have done an experiment, right? That's the research technique you must use to draw a causal conclusion as an experiment. Experiment has random assignment. Did they have random assignment? Well, yeah, they did. We randomly assigned 60 people. Have the researcher manipulates the IV. We can't take it as it exists in the natural environment. Yeah, we did that. We determined who got the training program and the placebo program. And we found a reliable difference. So that conclusion is justified. Sorry, little burps here. Okay, so might have some of those on the test as well. All right. Next skill I want to work on is identifying experiments and investigations. Okay, and remember what an experiment has to have is 1, random assignment, and 2, the researcher manipulates the IV. The researcher manipulates the IV. It has to have both those things to be an experiment. So there may be problems on the test where I describe how somebody did their research, and you have to tell me the independent variable, the dependent variable, and whether it was an experiment or an investigation. So let's try a couple of these. I'm just going to read them. Is a child's weight a function of family size? Random samples of 2-child and 6-child families were selected. The weights of all children were measured, and the means of the two sample groups are compared. what was the dependent variable in the study I just described? Well, the dependent variable, that's what we're measuring, and we measured the weights of the children. So the children's average weight, that's our dependent variable. What's the independent variable? Well, the independent variable was family size. That's what we chose the values for. Is that an experiment or an investigation? Well, we can't we didn't randomly assign people to be in 2 children or 6 children families, so since we didn't do random assignment, that has to be an investigation. That has to be an investigation. All right, let's try another one of these. Does quality of tires affect gas mileage? 40 new cars were randomly selected. 20 of the cars were randomly assigned to be fitted with expensive tires, and the remaining 20 were randomly assigned to be fitted with cheap tires. The same driver drove all 40 cars in turn, and each car's miles per gallon are recorded. We're interested in whether the mean miles per gallon is different for the cheap tires than for the expensive tires. All right, what's the dependent variable in the study I just read to you? Well, the dependent variable is the miles per gallon. That's what we were measuring. What's the independent variable in the study I just read to you? The independent variable is the type of tire. It had levels, cheap tires and expensive tires. So, is that an experiment or investigation? Well, that is an experiment. The cars were randomly assigned to get the cheap tires and the expensive tires. We manipulated the IV. We decided which cars were going to get which tires. And so that is a experiment, okay? So there might be some like that on the test. Now, we mentioned some that won't be on the test, and that is identifying main effects and interactions from graphs and tables. We did that. Okay, will not be on the test. Those will not be on the test. You're lucky. You don't have to worry about those. Reason is there's no way for me to put a graphic on the test, and so those require graphics. So we practice those in class, and that's a skill you should possess, but I will not have identifying main effects and interactions on the test. Okay, so now we're going to go to, since we practiced all the skills, we're going to go through general quizzing over the rest of the review sheet, and I'll try and make it so if you can answer all these questions, you should be fine on the test. And so, let's get out here. So, what I'd say is I can't have you write out the definitions. We had 3 new definitions in the definitions section. And I'll say over the midterm, number 2, review sheet, okay? So this is where I usually like at the, when we have the night review sessions, I'll go over the rest of the review sheet. That's what I'm going to do now. So I won't ask you to write out any of the definitions on the definitions section of the review sheet. Here's the review sheet. Here's the definitions section. You won't be able to write out any of those, but I could give you the term and ask you to come up with the name. Remember, we've got 3 new terms we haven't had before, and those are factorial design, interaction, and main effect, so I'd pay attention to those. Okay, what term has the following definition? Explanation for a phenomenon that can be falsified and that involves entities that cannot be directly observed. That's a theory. I'm going to do a 3 count in my head after I read each question and then give you the answers, how it's going to work. All right, what term has the following definition? Tentative statement about the possible relationship between observable variables. That's a hypothesis. What are the specific values of the independent variable that a researcher chooses to use in a study? Those are the levels of the independent variable. What advantage does the experimental approach have over other research techniques? What advantage does the experimental approach have over other research techniques? that allows the researcher to infer causation. An experiment allows the researcher to infer causation. What term has the following definition? Occurs when every member of the group to which we'd like to generalize our results has an equally likely chance of being chosen to participate in the experiment. That is random selection. What term has the following definition? Occurs when after the subjects for an experiment have been chosen. This occurs when each subject has an equally likely chance to be assigned to each IV level in a between subjects design or to each treatment order in a within subjects design. That's random assignment. Which is more important for external validity? Random selection or random assignment? The answer is random selection. Random selection is more important for external validity. What's more important for internal validity? Random assignment or random selection? Random assignment is more important for internal validity. What does an experiment have that a quasi-experiment does not have? Answer is random assignment. Random assignment. Which is greater in a positively skewed distribution, the mean or the median? The mean is greater in a positively skewed distribution. Which is greater in a negatively skewed distribution, the mean or the median? The median is greater in a negatively skewed distribution. Which is more affected by extreme scores, the mean or the median? The answer is the mean. Which one gives more consistent results across repeated samples, the mean or the median? The answer is the mean. That's why we use in our statistical tests. The mean is more consistent. Which one is easier to calculate if you have 1,000 scores? And the answer is the mean is easier to calculate. For the median, you'd have to put all the scores in order first, and that would take a lot of work. So for the mean, though, you just have to add up the scores and divide by the number of scores, so that would be less work. There are 3 problems with within subjects designs that are not problems in between subjects designs. What are those 3 problems? Answers are practice effects, sensitization effects, and carryover effects. What term has the following definition? Occurs when a subject's performance on the research task changes, either for better or for worse, as a result of experience with the task. And that is practice effects. What term has the following definition? Occurs when the effects of one treatment persist when another treatment is introduced. And the answer is carryover effects. Carryover effects. What term has the following definition? A method of assigning subjects to treatment orders in a within subjects design such that across subjects, practice effects are balanced. And the answer is counterbalancing. Counterbalancing. What function does a Latin square serve? In other words, what problem does a Latin square solve? A Latin square solves practice effects. It's a method of counterbalancing that is used to control practice effects. If you say carryover effects or sensitization effects, that is wrong. It only does practice effects. What term has the following definition? The extent to which your research provides a valid test of the relationship between the independent and dependent variables. And that is internal validity. Internal validity. If I increase alpha in an experiment, what effect would that have on statistical power? Increasing alpha in an experiment increases statistical power. If the statistical power of an experiment is increased, what effect does that have on beta? The answer is, if the statistical power of an experiment is increased, then beta goes down. Beta is reduced, because remember, power is 1 minus beta. If alpha is increased, what happens to beta? If alpha is increased, then beta goes down. The reason is alpha increases power. When power goes up, beta goes down. So increasing alpha decreases beta. Why is it desirable for an experiment to have high statistical power? The answer is to prevent type 2 errors. To prevent type 2 errors. What term has the following definition? It is logically impossible to prove that an independent variable has no effect on a dependent variable. And the answer is, can't prove the null hypothesis. What term has the following definition? The tendency for extreme values of a variable to fall closer to the group mean when retested. And the answer is regression to the mean. What term has the following definition? The extent to which the results of your research can be applied outside the research situation. And the answer is external validity. External validity. Definitions I'm going to give you now are very close to one another, so listen carefully. What term has the following definition? Occurs when subjects change their behavior as a result of their expectation that change should occur. That's placebo effects. What's it called when subjects change their behavior because they realize what the manipulations are in a study? That is sensitization effects. What if subjects change their behavior because they know they're being observed? That's a Hawthorne effect. What about when subjects change their behavior due to unintentional cues from the researcher? That's the experimenter expectancy effect, or the Rosenthal effect. What about when subjects, what are aspects of a study that indicate to subjects how they are expected to respond? And that's demand characteristics. Aspects of a study that indicate to subjects how they're expected to respond are demand characteristics. What problem does a single blind study solve? A single blind study controls for placebo effects. What two problems does a double-blind study solve? A double-blind study solves for placebo effects and Rosenthal effects. What is it called when the IV affects the DV only because the IV is something new? That's a novelty effect. What does MS treat measure in a between subjects one-way ANOVA? MS treat measures the variability in the DV due to the IV and error. What does MS within measure in a between subjects one-way ANOVA? MS within measures the variability in the DV due only to error. What does F measure in a between subjects one-way ANOVA? F measures how many times greater MS treat is than MS within, or if you prefer, it measures whether the IV affects the DV. Either way and either way might be on the test, so know both of them. F measures how much greater MS treat is, how many times greater MS treat is than MS within. It also measures whether the IV affected the DV. What term has the following definition? A naturalistic observation in which the researcher becomes a member of the group being observed. That is participant observation. What term has the following definition? A quasi-experiment in which a single group of subjects is tested on the dependent variable both before and after some experimental treatment. The answer is that's a time series design. Let me repeat that. Time series design, that's a quasi-experiment in which a single group of subjects is measured both before and after some experimental treatment. That's a time series design. Now that's the big term. Underneath it are the two time series designs you have to know for the test. Remember, the single group pre-test post-test design is a time series design, and the interrupted time series design is a time series design. So you got to know both of those for the examination. What term has the following definition? A statistic used to measure the direction and strength of the linear relationship between two variables. That's a correlation coefficient. What would it tell you about the relationship between two variables if you calculated the correlation and you found that R was equal to positive 16,432? The answer is the correlation was computed incorrectly, because remember, the biggest a correlation could ever be is positive 1, and the smallest it could ever be is negative 1. So if you got one that's greater than positive 1, you made a math error and you need to correct your result. So the biggest correlation can be is positive 1, smallest is negative 1. All right, what's it called when, as one variable decreases, another variable also tends to decrease? All right, that is a positive relationship. I tried to fool you by talking about decreasing rather than increasing. But what I said was, it says one variable decreases, the other tends to decrease. In other words, they're moving in the same direction. That's the key with the positive relationship. Are the variables moving in the same direction? So if I say as one variable decreases, the other tends to decrease, that's logically equivalent to saying as one variable increases, the other tends to increase. And both are a positive relationship. What's it called whereas one variable decreases, the other tends to increase? That's a negative relationship. That's a negative relationship when the variables move in opposite directions. If the correlation between a car's weight and the car's gas mileage is negative 0.4, what is the proportion of variance accounted for in gas mileage by weight? Again, if the correlation is negative 0.4. All right, well, if the correlation is negative 0.4, the way you calculate proportion of variance counted for is it's R squared. So you square negative 0.4, you get positive 0.16. And so that means it's 0.16 is the answer, right? So that's the proportion of variance accounted for. What if the correlation between a basketball player's height and the basketball player's number of rebounds is R equals positive 0.2? What is the proportion of variance accounted for in rebounds by height? Well, again, you have to take R squared, and since R was 0.2, you square 0.2, you get 0.04. So the answer is 0.04. Okay. So remember, proportion of variance accounted for is R squared. Also remember, if it's 0.3 or below, then you have to put the 0 beforehand. So 0.3 squared is going to be 0.09, but 0.4 squared is going to be 0.16. Okay, so if it's below, it's 0.3 or below, then you got to put the 0 beforehand. So remember that. What term has the following definition? Occurs when there's a floor or a ceiling effect on one of the variables in a correlation. Okay, that is range restriction. Range restriction. What term has the following definition? A description of the behavior or abilities of a single, usually exceptional individual. That is a case study. That's a case study. What term has the following definition? Research design in which the effects of an independent variable on a dependent variable are determined using one subject. And that's an experimental single subject design. Experimental single subject design. Okay, that's through the first part of the review sheet. That's the first half. Now, we're going on the second half. We got some lists that you have to know on the second half. So let's go over those. First one, what are the 5 factors determining statistical power? And I told you an acronym to help you remember that. CAVES, right? C is correlation between the IV levels. A is alpha. V is variability in the DV. E is effect size. And S is sample size. So it makes the acronyms CAVES, C-A-V-E-S. Hardest one is correlation between the IV levels. All right, why doing ANOVA instead of multiple t-tests? Well, the reason is, number one, usually multiple t-tests would be more work than doing an ANOVA. And the second reason is that multiple t-tests inflate the type 1 error rate. Next question. What are 2 reasons why correlation cannot be used to determine causation? Well, the first is the directionality problem, which says that it's often difficult to know which variable was cause and which was effect. That's the directionality problem. Second reason is the third variable problem. There may be a third unmeasured variable that's responsible for the relationship. That's the third variable problem. What are the 3 mathematical limitations of correlations that we discussed in class? All right, there were 3 of them. The first one is they're poor at capturing nonlinear relationships. The second one is they're greatly affected by extreme scores. And then the third is they can be lowered by range restriction. It's important to know that the effects of range restriction on the correlation would be to lower it. Last one is the problems with all single subject experimental designs, and there are 4 of those. So the first one was likely type 1 and type 2 errors. Second one is likely placebo effects. Third is generalization difficulties. And fourth is experimenter bias. So, the answer, well, what are the 4 problems with all single subject experimental designs? That is likely type 1 and type 2 errors, placebo effects, generalization difficulties, and experimenter bias. Okay, well, I've asked you just about all the questions that could be on the test, essentially. Like I said, there are going to be more of the questions which you have to think about, I think. But that should be ready for you starting at noon on Wednesday. You've got until Thursday at 1 to get it done this week. So you need to get that done this week. Okay, then also, if you saw Friday's lecture, it was just going over the test. It was one of the optional lectures in the class, so there won't be any lecture on Friday. So this review lecture is the only lecture that I'm going to film this week. All right, so good luck on the test on Wednesday. And remember, if you got questions, questions about anything for the test, my email address is ecooper@iastate.edu. All right, good luck, and I'll talk to you again next week.